A very good morning. My name is Aditya Tripathi, and today I'll be talking about nonlinear support vector machine. So, what is a support vector machine? Before understanding nonlinear support vector machine, let's first understand what SVM are. So, SVM is a fast and dependable classification algorithm that performs very well with a limited amount of data. Now, what is a classification algorithm? The basic premise is that classification is algorithm is one which classifies given input into classified groups in which the aim is to separate all the items in identifying group and no two group be similar. So like if we have this ice cream and cake, then they should be separate. Classification algorithm in general is a function that weighs the input features so that the output separates one class into positive values and one into negative. So these are all weighted so that they are classified into three groups. Now, it is a supervised machine learning algorithm used for classification. Supervised only means that it uses input-output pairs. Now, found by Wapnick in 1990s, support vector machine splits the data point into two sections, classifying the data using a line called decision boundary or hyperplane. This decision boundary is the separating line which separates the classified into two more groups based on how many classifications we are doing. Now there are a lot of classification algorithms like naive Bayes, decision tree, support vector machine, random forest, k nearest neighbors, but we'll be looking at support vector machines. Now let's take an example of SVM to understand this procedure better. Suppose we have two tags, green and blue, with the features x1 and x2. A support vector machine will take these data points and output the hyperplane that best separates the tag. Now, how is this done? What we do is we take the features and plot a graph of the tags. Now, the tags which are the closest to its opponent are the support vectors. So, for this group of green tags, this green tag is the support vector. Similarly, for this group of blue tags, this blue tag is the support vector. Now, using the support vectors, we find the distance between them and the hyperplane. Now, this distance is called maximum margin, and the line which goes through this maximum margin is the hyperplane. Now, the basic question that comes is that if we have two groups like this, we could have made a line anyhow like this or this or this. The orientation could be anything. But then why did we choose only this line as the hyperplane and not this or this? The reason being that we find the maximum margin, that is the maximum distance between the support vectors. There will be only one or so maximum margins that will be found, and only that respective hyperplane in that maximum margin will be used for classification in the SVM algorithm. Now, let's move forward. The nearest points to the opponent class, as I said, are called support vectors. Support vector from both the classes give the margin. For deciding hyperplane, we maximize this margin to select a hyperplane. This is called maximal margin hyperplane. This maximal margin hyperplane is the one we use for classification. The data can be two types. It could be linearly separable or non-linearly separable. A linearly separable data will be such that a straight line can pass through the data and separate it into two groups. This is what we want to do in order to classify our data. But you can also have a data set such that no matter how you make the hyperplane and how it divides, the chance of getting one of the group is 50% or less than 50%. So if I'm looking for the red tag, the chance or the probability that I'll get it on the topmost side is 50% or less than 50%. This is no classification, this is only blind luck. Now In order to classify, what we can do is we can find a hyperplane using the features of the features. Now, if we try to do that, what will happen is we'll end up with a very computationally heavy task. This will be an NP hard problem. Instead of this, what we can do is we can move to a higher plane. Or suppose this was XY axis, we can move to Z axis, and we can from Z axis look top down in order to find a hyperplane that will convert the second dimension. So we move this, we'll understand better with an example, I guess. So if we have vectors through which a linear hyperplane cannot be made, move to a higher dimension. So if we were like this, we move to a higher dimension, say Z dimension, which has an equation x square plus y square. If you notice, this is equation for circle. So we move to a higher dimension, and there we use the procedure as mentioned before to construct an hyperplane. Now, using the best possible hyperplane, we map this hyperplane to our original dimension in order to get the best hyperplane possible and classify the data into two parts. This is called the kernel trick. Now let's discuss what the kernel trick is. Now basically what kernel trick is used for is to move to a higher dimension. That is transformation from this dimension to the next dimension. This could have also been done simply. The trick I was telling you of using feature of features. Now that would have been a computationally heavy task. So instead of doing that, we use a kernel function. What kernel function does is it actually takes the dot product of the attributes using a function called kernel function to provide the same output. Now that is not computationally heavy and can be done by our computers easily. Now finding out higher dimension plane transformation can be computationally very heavy. That is an NP hard problem. This can be avoided by using a kernel function. Kernel function doesn't use the actual vector but the dot product between them. This can sidestep the expensive calculation for the new dimension. That's basically what we want. Now let's take a numerical example to understand this better. Suppose there's a vector x. Now x has two attributes x1 and x2. Now let there be a function, kernel function k, with attribute xi and xj, with kernel function being 1 plus xi dot function xj square, the whole of square. Now xi has two components xi1 and xi2, whereas xj has two components xj1 and xj2. Now let's find the dot product. We get this, which is when solved basically xi dot xj plus 1 the whole square should be square, which is actually the transformation of xi dot the transformation of xj, which is exactly equal to kxi xj. Hence we can sidestep the computation using our kernel function. Now there are a lot of common kernel functions used, being linear kernel function, polynomial kernel function. The t here indicates the dot function. Dot operation is indicated by t here. So x dot y plus 1 the whole to the power p is the polynomial function. We just use this in our example, square here. Gaussian or RBF kernel, Laplacian kernel, sigmoid kernel, and Mahalanobis kernel. There are also many more kernel functions, but that is outside the scope of this lecture. Now, what are the pros and cons of SVM? SVM is efficient and works well for small datasets and in higher dimensional spaces where the non-linear datasets are small. So if you have a small dataset and you move to a higher dimension, like over here we move to 6 dimension, each vector has a 6 dimension, then this algorithm is really efficient. Now it is also effective in solving dimension when the number of dimension is larger than the number of samples. If the number of dimension is larger than sample, then it is efficient. Now it is not sensitive to overfitting. high training time and doesn't work very well when there is noise is the con that SVM faces. Now, what are the use case of SVM? Text classification, detection of spam, and sentiment analysis. Also, along with this, aspect-based recognition are the uses of SVM we find in practical life. Thank you. That's the end of the lecture.